I want to thank Brigham Young University and the College of Physical and Mathematical Sciences and the Alumni Association and the Chicago branch of the Alumni Association headed by Greg and Jill Brim for giving me this opportunity. I really do appreciate it. So I'm going to be talking about in vitro fertilization, the past, the present, and the future. But I have a kind of a subtopic also, which is, can we prepare for the unknowable future? And I'm going to give two answers to this question. I'm going to give the first answer fairly early in my lecture that's kind of tentative, probably of some value, but you know, it's not 100% reliable. And then I'm going to give the second answer to the question near the end of my lecture, which is final and absolute. Well, when we grow up, we all have dreams about what we want to do. Best kind of summarized here by Mark Twain. Now and then we had a hope that if we lived and were good, God would permit us to be pirates. I never really wanted to be a pirate, but, and I didn't know Eastern Carolina were the pirates, but anyway. I knew I wanted to be a chemist from when I was 9 years old. And this isn't a picture of me, of course, I just dragged this off the internet, but it could have been me. And that chemistry set there looks awfully familiar to me. You know, the trouble with being a young chemist is you really, well, let me back up. This is one experiment I used to love to do. Oops, sorry. And that is, you know, you can get, and I used to do this, I remember doing this at jamborees, scout jamborees, and having people swift the chlorine and putting a little match up into the hydrogen tube and it explodes and you get water coating the tube and you know, get sodium hydroxide in the solute and you can feel. But my friend Lynn Christensen and I were kind of upset by the fact that we couldn't really get the chemicals we needed to do the experiments we wanted. We couldn't get things like sulfuric acid and nitric acid and hydrochloric acid. They wouldn't sell them to responsible young teenagers like us, and our parents weren't very helpful either. So we decided we would modify this experiment one day, and instead of using a direct current, we thought, well, maybe we'll use an alternating current. And then maybe we'll get a little bit of chlorine, a little bit of hydrogen, and maybe they'll combine and we'll get hydrochloric acid at each electrode. And so we got an extension cord, and we cut off the end of the cord that has the sockets on it, stripped the wires, attached to them. We did have these carbon electrodes, and got everything set up in a big, I think, Pyrex dish. And then we plugged the extension cord into the wall. And we got this massive roiling, and then, of course, the circuit breaker was tripped. So we were disappointed. And we thought, we fooled around a little bit and tried it one more time, and the same thing happened. So we never were able, and I'm sure that if we got the current to go through continuously, we would have started with a sodium chloride solution and we would have ended with a sodium chloride solution. But at the time, it seemed like a good idea. So I went to BYU, determined to have a chemistry major, and I took a semester of freshman chemistry from Tracy Hall. And then later at BYU, I had the opportunity to be a research assistant in the high pressure lab. And Dr. Hall featured with one of his tetrahedral presses. And it's interesting, I worked in the high pressure lab. The director of the project was Dr. John Cannon, who was on the faculty here at BYU for many years. And we were working on synthesizing high temperature superconductors. That was the idea. And I worked with a couple of people. On the left, you can see Dr. Paul Farnsworth. He worked in the lab with me. I'm sorry, on your right. On your left is Dr. Jeff Taylor. And it's interesting to see how I think this was a tremendously valuable experience for all of us. Paul, as you know, is a professor and former chairman of chemistry here. Jeff also went to medical school. He became an orthopedic surgeon. And orthopedic surgeons are really engineers at heart. And he later co-founded Dimacron, which is a company that makes artificial joints using polycrystalline diamond, using synthetic diamond. So he's probably the one who benefited the most from his years in the high pressure lab. And Jeff will tell you that diamond is the perfect substance for artificial joints. It's very inert. It's very hard, so it doesn't wear. And it has a very low coefficient of friction. So diamond on diamond is very smooth to move. And that's a little bit about my experiences in the high pressure lab and some of the great people I worked with there. Now, my senior year, I took a couple of classes from Smith Broadbent, who was a professor of chemistry. I was very interested in organic chemistry. And I took, I think it was called organic synthesis or advanced organic synthesis, and I took systematic identification of organic compounds, which was a lab class from Dr. Broadbent. I don't know what it's called now. But anyway, I learned something really important from Dr. Broadbent. I learned I was much better at learning chemistry than I was at doing chemistry. And so I sort of decided at that point, I started to think, and I decided maybe I would go to medical school. And I think it turned out to be a very good decision for me to do that. But I was tremendously influenced by the great professors I had here at BYU. I've shown you just a couple, but many, many tremendous professors. There probably aren't very many people who have some think back with fondness on their organic chemistry tests. This was Morrison and Boyd. I don't know if there's still an iteration of Morrison and Boyd around these days or not, but it was the organic chemistry text I used. My friend Jeff Taylor had a friend named Claire Taylor, no relation, but a good friend, and Claire was taking organic chemistry and felt like she needed a tutor, so I volunteered. And I think we both learned a lot about chemistry that semester, and the chemistry was fantastic. And so we were married in 1976 between my freshman and sophomore year, first and second year of medical school. So that's kind of the run-up to this talk. So now we're going to move on and talk about the recipe for in vitro fertilization. So Louise Joy Brown was the first child born from in vitro fertilization, and she was born in July 1978. That was between my third and fourth year of medical school. And so it really caught my eye. I'd always been interested in endocrinology, and I decided I was going to pursue this field. Now, her birth was the result of a very successful collaboration between Dr. Edwards, who was a basic scientist, and Dr. Steptoe, who was a clinician. And in vitro fertilization is a great example in medicine of the great value of collaboration between basic sciences and the clinical sciences. Dr. Edwards received the Nobel Prize. He was the sole recipient of the Nobel Prize in medicine in 2010 for the development of in vitro fertilization. Dr. Steptoe had died, I think it was in 1998. What was IVF like back in the early days versus what it's like now? In about the first 4 years of in vitro fertilization, 5 years, the number of egg retrievals reported worldwide was about 825. There were 32 deliveries. So that's a 4% live birth rate. It's very low. And in fact, there were some studies back in the early days of IVF that showed you were more likely to have a baby waiting for your IVF procedure than you were actually having your IVF procedure. But it has changed dramatically. In 2013, worldwide, there were about 1.5 million IVF cycles, 350,000 live births, which is a 23% live birth rate per cycle start, and that's all comers. And those cycles include both fresh and frozen embryo transfers, which we'll talk about later. So IVF is far and away the most effective infertility treatment. Over 5 million IVF babies have been born since 1978. In Japan and some European countries, 3% of all births are from in vitro fertilization. In the United States, 1.5% of all births are from in vitro fertilization. So I want to talk a little bit now about what's involved and how things have changed in vitro fertilization from what it was back then. I did my fellowship in reproductive endocrinology from 83 to 85, so I was really near that beginning end when I was actually practicing this, but I've been alive through the whole history of human in vitro fertilization. So back in the former days, this pointer isn't showing up on the screen very well, but on your left, the reason in vitro fertilization was developed was for Tubal disease. And on your left, on the top, is a picture taken by laparoscopy. And To orient you, it's like you're looking from the patient's head down towards her toes. The probe there is on the posterior uterus. On the left is the left tube and ovary. On the right is the right tube and ovary. The ovaries are pearly white. And you can see the fallopian tubes are very thin. They have these beautiful fine little fimbriae at the end. They're well vascularized, nice and pink. Now the slide below you is a closer up view, but it's of the left fallopian tube. And you can see that tube is very dilated. It doesn't have much blood flow to it. It's not pink at all. And its walls are paper thin. And you can't see it, but internally, the internal architecture of the tube has been destroyed. So you could say, well, let's operate on this tube, open it up, and see if we can then resolve the patient's fertility. And in general, tubal disease is almost always bilateral, although I'm just showing you one tube here. You can do that, but the results are terrible. And that's why in vitro fertilization was developed. So we still do in vitro fertilization for tubal disease, although in our patient population, it's a relatively uncommon indication. It's also become the best treatment for male factor infertility. So a man with an extremely low sperm count, and I'll talk about this later, doing in vitro fertilization has a dramatic improvement on fertility outcomes. And it's also the procedure of last resort. When other simpler procedures haven't worked, there's a large category of patients we call unexplained infertility. We try simple things first. If that doesn't work, then we go on to in vitro. And it's extremely efficacious in those patients as well. Now, back in the early days, and we're going to get into a little reproductive physiology here, and I hope everybody can stay awake. But back in the early days, in vitro fertilization was done in a natural cycle. In a natural cycle, a single follicle is produced in one or other ovaries. The cycle was monitored to see when to look for the onset of what's called the LH surge, which indicates ovulation is about 36 hours away. A single egg was usually produced, 0.7. So when they did the laparoscopic egg retrievals back then, 70% of the time they were able to get an egg. And of those eggs, only about 2/3 will fertilize. So hopefully they would end up with a single embryo. We now do stimulated cycles. We have the patients take injections of LH and FSH, those are gonadotropins, the hormones that make the follicles grow. We get multiple follicles. We trigger ovulation. Hopefully we get multiple eggs and therefore multiple embryos. I should be able to do this. So at the beginning, these are ultrasonic images of an ovary using high frequency ultrasound to image the body. This is the ovary right here, and all these little black holes are little follicles in the ovary. This is a young, healthy ovary. At the beginning of the menstrual cycle, there's several little follicles, maybe 3 or 5 millimeters in diameter. One of those follicles will go on to become a dominant follicle. It will grow to be about 20, 25 millimeters in diameter at the time of ovulation, about 14 days later. These other follicles all become atretic. They die, they fade away. And then if ovulation occurs, the patient doesn't become pregnant, then at the beginning of the next cycle, there's another new cohort of follicles here, and one of them becomes a dominant follicle again. Now what happens is when the dominant follicle grows, this follicle isn't empty. It looks empty, but it's full of granulosa cells and, of course, the egg. The granulosa cells make estrogen, estradiol, and as estrogen levels rise, follicle-stimulating hormone, which is a main hormone that makes the follicles grow, it declines in response to estrogen. It's a classic endocrine negative feedback mechanism. And because it declines like this, if you're the follicle that's in front, you win. But if you're the follicle that's behind, you become atretic. And then when estrogen levels get high enough, long enough, that's sort of a signal to the pituitary gland that says, hey, you know, I'm a mature follicle, I'm ready to go. And so the pituitary gland sends out a surge of luteinizing hormone, LH, and this is the surge that triggers the final maturation of the egg and triggers ovulation. So when they were doing natural cycle IVF, they would bring these women into the hospital about here, check levels of LH in their urine every 6 hours or so, and then when the onset of the surge, they would do the retrieval about 34 hours later. So what do we do now? How does it work now? So here again is an ovary at the beginning of the cycle, all these little follicles. In a natural cycle, one of them becomes a mature follicle, one egg is released. But when we do in vitro fertilization now, the patient takes injections of luteinizing hormone, follicle stimulating hormone. These are synthetically produced, and because we give much higher levels of FSH and maintain a high level of FSH, we basically rescue all of these follicles. So this, after about 10 days or so of stimulation, this is what the ovary looks like. So we have all these follicles that we hopefully can collect eggs from. And so that's been a dramatic improvement in in vitro fertilization. And this happened pretty early. By 1981, we weren't doing natural cycle IVF anymore. They were doing stimulated cycles because we could retrieve so many more eggs. Okay, now how do we do the egg retrieval? Well, early on it was done by laparoscopy. Requires an operating room, requires general anesthesia, and because they were monitoring natural cycles, you had to be available 24 hours a day. You may be doing the laparoscopy at 2 o'clock in the morning or 4 o'clock in the morning, and face it, the reason everybody went into this field is they didn't want to deliver babies in the middle of the night, and so we don't want to deliver eggs in the middle of the night either. So that's why we went to the stimulated cycle, and then you could trigger ovulation. You give them a surrogate LH surge at 9 o'clock at night, and then you do the retrieval at 9 o'clock in the morning 2 days later. It's much more civilized. Now we do ultrasound-guided aspiration of the eggs from the follicles. It's an office procedure, can be done under conscious sedation, and we do the retrievals in the morning. So this is a diagram of a laparoscopy. This is the abdominal cavity right here. Before doing the laparoscopy, a needle is inserted, and the abdominal cavity is filled with carbon dioxide to separate the wall of the abdomen from all the contents. Now, what you don't see here in this diagram is all the bowel that's all over. And when you first look in, when you do a laparoscopy, all you see is bowel. But you can get the bowel out of the way, and then you see the uterus, fallopian tube, follicle here in the ovary, and you can put a needle through here, aspirate the follicle, and collect the eggs. And we did this also early when we were doing stimulated ovaries. We'd have these large stimulated ovaries, we'd put the needle in and collect. But it's much easier, and by 1985, everybody was using ultrasound to collect the eggs. This is another diagram. This is the uterus here. This is an ovary in cross-section. This is a vaginal probe ultrasound. It goes up into the vagina against the vaginal wall. And you can see there's a guide on here that a needle goes through the vaginal wall into the ovary, and you just suck the fluid out of every follicle you can see in each ovary. It's very simple to do. I don't like to admit that, but it really is. So here's what you see on ultrasound. When you're holding the probe in one hand, the needle in the other, going through the needle guide, this is the needle right here in the follicle in the ovary, and it's connected to a vacuum pump, which then pumps the follicle contents into a tube, which is then handed off to the lab where they look for the egg, and you just move from one follicle to the other. It works very nicely, very easily. Patients are very comfortable, they're under conscious sedation, they wake up very quickly, it works very well. Now, the other thing that's been a dramatic change, and this is really where all the magic happens. What I do is pretty simple. All the magic is what Dr. Edwards worked on, and many, many people since him, is the Embryology Laboratory. Back in the early days of IVF, everybody made their own culture media, and they all made or jerry-rigged their own incubators for incubating the embryos. And they would generally only culture to day 2 or day 3, day 0 being the day of the egg retrieval. So day 1 is one day after, day 2, day 3. They'd culture to day 2 or 3 and then do the embryo transfer. Now we have commercial, very high quality, commercially available culture media and incubators specific for use for IVF. And this makes a huge difference to have these high quality, commercially available cultures. We oftentimes now culture out to day 5 instead of day 3. This is when the blastocyst forms, and I'll show you a picture of this. And we get a better idea by culturing out further which embryos are more likely to result in a successful pregnancy. Probably the most important advance made in the laboratory since the beginning of IVF is ICSI, which stands for Intracytoplasmic Sperm Injection. This is the treatment now for male fertility. The other thing we can do very efficiently now, so ICSI became available in about 1992, was first reported, and it's because anything that works well on IVF spreads like wildfire. Within a year or two, everybody was doing ICSI. Things that don't work so well, there's all these arguments about and all these papers about, and you know, but something like this spreads so quickly, you know it's good. We're also, the first pregnancy from a frozen embryo was about 1983, I think. But we weren't very effective or very efficient at it. Now we're very efficient at freezing both embryos and oocytes. So I'm not going to talk about this more, but the ability to freeze an egg, so we collect the egg and instead of fertilizing it, we just simply freeze it, has allowed us to provide an option for young patients who are about to go chemotherapy, which can be very damaging to eggs, to freeze eggs and store them and thus have a hope for fertility afterwards. And I could give another 50-minute lecture on that, but I'm not going to talk about that more today. So here is a picture of some embryos. And this is a zygote. This is shortly after fertilization. It's still a single cell. This is the egg. But inside are two little nuclei, one from the sperm and one from the egg. By 24 hours after fertilization, the embryo has divided once into 2 cells. 2 days after fertilization, it's divided twice into 4 cells. 3 days, divided 3 times, 8 cells, the most advanced embryos. And then the embryo undergoes a very rapid proliferation, multiplication of cells. The cells become less distinct. And by day 5, you have what's called a blastocyst. A blastocyst is a sphere. It's fluid-filled. The cells that form the sphere are called the trophectoderm, and they develop into the placenta and the membranes of the pregnancy. Inside the blastocyst is this little lump of cells here. This is the inner cell mass. This becomes the baby, okay? And this inner cell mass is made up of, because I'm going to talk about this later, is made up of stem cells, embryonic stem cells. Any cell in this inner cell mass can develop into any cell in the body. 1 day later, day 6, the blastocyst hatches. This is, you can't see it, but the blastocyst is surrounded by a membrane called the zona pellucida, which is also around the egg. That's the zona pellucida right there. Day 6, it hatches out. Here it's coming out so it can implant in the lining of the uterus. So here's intracytoplasmic sperm injection. I hope you can see this. So what happens is the embryologist takes a microscopic glass needle and draws up a single sperm right here into the needle. The needle is then advanced through the membrane of the egg into the cytoplasm of the egg, and the sperm is just injected into the egg. This is a holding pipette here to hold everything in place. It was thought in the early days of IVF, if a man had a really low sperm count, that because we're just going to add the sperm to the dish right on top of the egg, maybe we could overcome male factor infertility. But we couldn't do it. It didn't work, or not very well. But doing ICSI, we can virtually completely overcome any male factor issues. So the pregnancy rates with ICSI are the same, and live birth rates are the same as if the sperm count were completely normal. So this has revolutionized fertility treatments. Women will complain, of course, that they're the ones that have to go through all the work for this male treatment to work, and that's true, but that's the best we have right now. So I want you to concentrate on these middle 2 bars right here. This is going back to talking about embryo freezing and showing how good we are at it now. So these are live births from embryo transfers. The kind of orange bars are fresh embryo transfers, and the blue bars are frozen embryo transfers. So you can see 37%, 38% of frozen embryo transfers, 36% of fresh result in live births. Now this is all comers, not divided by age. So we're really, really good at freezing embryos now, and this gives us a lot of opportunities to help people. Now I want to talk briefly about the embryo transfer. This is the final step of IVF. We've created the embryos. They've been in culture for 3-5 days. Now we have to get that embryo into the cavity of the uterus. In the old days, it used to be done blindly. Now we use ultrasound guidance. We use catheters that weren't specifically designed for embryo transfer because they just weren't available. They tended to be hard, stiff, and could potentially damage the lining of the uterus. We now have catheters specific for IVF. They're very soft and flexible. Back in the old days, we tended to transfer multiple embryos, and that's because we weren't very good at doing IVF. But if the patient became pregnant, she was at risk for having multiple births. And that's the main problem with IVF. The main risk of IVF to the mother and the baby is multiple births, having more than one baby. Even twins have a very high risk of being born prematurely and having all the problems that can happen from that. So now we have we use ultrasound guidance to guide, and I'll show you a picture of that, to guide our catheter placement so we can get it in exactly the right spot. The catheters are specific, like I said, and we are going more and more to transferring a single embryo, especially in younger patients. If we transfer 2 embryos in someone who's 32 years old and she becomes pregnant, she probably has a 30% chance or higher of having twins. If we transfer a single embryo, she only has a 1% to 2% chance of twins, which is identical twins, which we can't fix. We can't fix that yet. So here when we do ultrasound-guided embryo transfers, the probe is on the abdomen. Fluid is black on ultrasound. This is the bladder. It kind of gives us a window. Here's the uterus right here. This bright white line is a catheter coming up through the cervix, being guided by the doctor into the cavity of the uterus. This is the cavity right here. And so this is right in the sweet spot right here where you want the embryos to be. These are air bubbles that are on either side of the embryo. You can't see the embryo on ultrasound, of course, but you can see these little air bubbles. So you can tell when the embryo has been released into the cavity. So that's how we do embryo transfers now, and it works very smoothly. All right, so now we're going to talk about the fun part, okay? We still have a little bit of time. We're going to talk about the future of in vitro fertilization. And I'm probably just as reliable as this guy is. I pulled this off the internet. This is some guy that makes predictions about NBA basketball, but it was the best thing I could find. And I'm going to talk about two things. I'm going to talk about the biological clock, oocyte depletion, so the oocyte is the egg depletion, oocyte depletion, and aging. And I'm going to talk about the genetic revolution, which is really dramatic in vitro fertilization. So here's the deal. I'm sure you've heard of the term the biological clock. I don't know how clearly this comes up, but this is weeks gestation right here. 40 weeks gestation is term. A woman has the maximum number of oocytes in her ovaries when she's about 24 weeks gestation, 16 weeks before she's born. From that time on, there's a constant depletion of oocytes, and there's no regeneration of oocytes. There's been some controversy about that, but as near as we can tell, there's no regeneration of oocytes. There's just this gradual decline, so that at birth, there's 1 to 2 million oocytes in both ovaries combined. And by puberty, there's only 300,000. If you do the math, about 0.1 of 1%, about 1 in 1,000 eggs will be released at the time of ovulation. The others become atretic, they fade away, they die, okay? So, and then 300,000 down to menopause, just maybe 100 or so in each ovary. So there's this constant decline in number of eggs. And the reason it's a problem for us is that the more eggs there are in the ovary, the more of them that become mature enough that they can respond to the stimulation with gonadotropins, and so the more eggs we collect. So as the number of eggs in the ovary declines, we get fewer and fewer eggs when we do the egg retrieval. So this is the biological clock as it accounted for by the number of eggs in the ovary. Now there's another and even bigger problem, and that's the aging of the egg. So the eggs you have in your ovaries have been there since before you were born. So as you get older, the egg is older. You don't get any new eggs. And what happens is oocytes have to undergo meiosis. That's the process where the cell goes from having the normal number of chromosomes to 1/2 the normal number of chromosomes. So that when the sperm combines, the embryo ends up with the total correct number of chromosomes. So it goes from 26 to 23, and then at fertilization back to 26. What happens is, as the egg gets older, its ability to undergo meiosis successfully diminishes, and it ends up with too many or too few chromosomes. That's called aneuploidy. It's too many or too few chromosomes. And you can actually do biopsies of blastocysts, and you can see how many of the blastocysts. Now, these aren't eggs, but these are embryos that have been generated from eggs. But the data is very, very strong that aneuploidy is almost exclusively an egg issue. If you look at the percentage of blastocysts that are aneuploid up to 35, it's only 30 or 35%. But by 40, it's all the way up to 60%, and by 42, it's up to 75%. So not only are you facing this problem of having fewer eggs when you do IVF, you can retrieve fewer, but they're less likely to be chromosomally normal. And that's the biologic clock. And that's dramatically displayed in clinical data. So this kind of orangish line right here is a chance of having a live birth per embryo transfer using fresh embryos based on a patient's age. So this is 35 right here. Up to 35, it's pretty close to 50%, but then there's this dramatic decline, so that by 40, it's about 25%, and by 42, it's about 15%, and by 44, it's just 2 or 3%. So there's this dramatic decline in success with IVF with age. Now, what's this blue line? Well, this blue line are women who have decided to use an egg donor. Egg donors are recruited anonymously. They're young, they're under 30. Their ovaries are stimulated, their eggs are collected. They're then fertilized with the sperm of the husband whose wife wants to have a baby, of the couple who want to have a baby. And then the embryo is put back into the mother's womb. So she carries a child, delivers a child, but it's not her genetic child. But you can see there's no impact of age on success rate with egg donation. And that's why some women do decide to do that. Well, what's going on here? I actually borrowed this slide from Eli Adachi, who used to be chairman of OBGYN at University of Utah and then became dean of the medical school at Brown. But anyway, so this is a mother mouse, and this mouse was born from an egg that was made from an induced pluripotent stem cell. Now, what are induced pluripotent stem cells? It's a cell from an adult, like from the skin or from the bone marrow, that's been differentiated. It can be made to de-differentiate into an induced pluripotent stem cell. So it becomes like an embryonic stem cell. It can develop into any cell in the body. And then once it's been de-differentiated, it can be redirected down any path you want. And this mouse came from an oocyte that was derived from an induced pluripotent stem cell, from a somatic cell, a body cell, from an adult mouse. And this mouse was fertile. These are her kits, okay? So this technology works really well on rodents. But it's very possible that this is one of the futures of in vitro fertilization. Now I want to talk a little bit about the genetic revolution in vitro fertilization, because there's probably, well, you know, everybody says it's about their own field, but there's probably no field more directly impacted by genetics than in vitro fertilization, because this is where therapy and genetics meet. So last spring, Claire and I were able to take a trip to Scotland and England, and here I am outside of the Eagle, which is a pub in Cambridge, very near the old Cavendish lab, which is a very famous lab. And it's the lab where Watson and Crick did their work on the structure of DNA. So if you go inside the pub, the Eagle, Cambridge, discovery of DNA, on this spot on February 28, 1953, Francis Crick and James Watson made the first public announcement of the discovery of DNA with the words, "We have discovered the secret of life." Throughout their early partnership, Watson and Crick dined in this room on 6 days every week. So I guess the 7th day they rested. Of course, this isn't quite correct. They didn't discover DNA, but they discovered the structure of DNA, and that was critical in understanding how it was easy for DNA to replicate whenever a cell divided. So how do we use genetics in vitro fertilization? We do it a lot presently. We can actually create embryos. Let's say a couple are both carriers for cystic fibrosis. That means they have a normal gene and a cystic fibrosis gene. They have a 1 in 4 chance that their offspring will have cystic fibrosis, 2 abnormal genes. Well, you can create embryos, you can biopsy the embryos, and only transfer the embryos that don't have cystic fibrosis. So you can do that. And you can also diagnose chromosomal abnormalities in embryos and only transfer the ones that are chromosomally normal. The future is the alteration of abnormal or less desirable gene or genes within the embryo. And that, of course, is a little more dicey. So how do we use genetics in IVF? Well, the first step is to biopsy the embryo, genetic analysis of the biopsied cells, and transfer to normal embryos only. It was first done in 1990 for looking at Y-specific DNA for X-linked disorders. So disorders like certain kinds of hemophilia, certain kinds of muscular dystrophy. If the embryo had a Y chromosome, that it had a 50% chance of being affected, so they would just transfer the embryos that were XX, that were female. But it was also first done in 1990 for autosomal recessive disorders. It was cystic fibrosis. Now, the field has expanded dramatically since that time. We usually biopsy blastocysts now because blastocysts are very resistant to biopsy. It doesn't seem to hurt them any. So here, again, is a blastocyst. This is a holding pipette here. Here's the inner cell mass right there. So you always biopsy opposite the inner cell mass. This is a little bit of the trophectoderm, the cells that develop into the placenta and membranes, being drawn up into a biopsy pipette. Then a little laser is used to cut them off. And that's how you do the biopsy. So again, we're in London, okay? I'm riding in the subway in the tube, and I look up and I see this big ad in the car of the subway. Why is IVF not more successful? Can you pick which of these embryos made a baby? And there's 2 very beautiful, nice-looking 8-cell embryos. And of course, you can't tell by looking at the embryo which embryo is most likely to result in a baby. That's the problem. That's one of the challenges of IVF. Looking at the morphology of the embryo gives us some idea, but it's far from perfect. And this shows you what a big-time business IVF is also. They advertise about it in the tube. So this is what they are referring to as what we usually call comprehensive chromosomal screening. So you biopsy the blastocyst, you freeze all the blastocysts you biopsy, which we're very good at doing now, and then the biopsy cells are tested to see if they're chromosomally normal. And then you only transfer the blastocysts that are chromosomally normal in the subsequent cycle. Because the ones that are abnormal, one, either won't implant, or two, if they do implant, they'll result in an early miscarriage, which is an unfortunate outcome. Or if it results in a continuing ongoing pregnancy, you could have a child with Down syndrome, for example. So you only transfer the chromosomally normal blastocyst. Now, does this work? Well, it depends on how you look at it. And this is a fairly early study. So these are all patients who had a single blastocyst transferred. These patients, there was no comprehensive chromosomal screening done. These patients, there were. Patients under the age of 35, now this wasn't a randomized trial or anything, but the ongoing pregnancy rate or live birth rate was 71% if the embryo was chromosomally normal, and it was 47% if it was abnormal. Now, these others weren't significant. These other age groups, 35, 37, 38, 40, 41 and older were, but it does remain, if you look enough, it's statistically significant. Now look at this. So I was telling you if you're 42 and you had an embryo transfer, you had maybe a 15% chance of a live birth. Look at this. This is 41%. That's fabulous. That's so much better. But I want to make a couple of points here. One, being chromosomally normal doesn't guarantee a normal embryo. There's only 71%, even in young patients, of chromosomally normal embryos that will result in a pregnancy. And it gets worse as you get older. So again, we're looking at this age thing. It's 41% of chromosomally normal embryos. Now it may be a little higher now that result in an ongoing pregnancy. The other problem is, of course, this isn't 41% of everybody who started an IVF cycle. This is 41% of patients who had a chromosomally normal embryo to transfer. So if you do the math, this may be 10 or 15% of the original patients, because not everybody is going to get enough. Some patients may have embryos that don't develop the blastocyst, and some patients may have 2 or 3 blastocysts, but they're all chromosomally normal. There's a 75% chance that each blastocyst is chromosomally abnormal. So the trouble with comprehensive chromosomal screening, there's been a tremendous amount of publicity about this, as I showed you, but it works best for younger patients, and they're those who need it least. Patients 40 years and older may produce only 1 or 2 blastocysts, pay $3,000 in the United States for comprehensive chromosomal screening and not have a blast to transfer. The one advantage to it is it may decrease the miscarriage rate. So if you transfer, the miscarriage rate is lower than if you don't know the chromosomal makeup of the embryo. But there's no evidence that it increases the ultimate live birth rate in younger or older patients, given our ability to freeze blastocysts. So what I'm saying is, suppose we have a 32-year-old patient. She has 2 beautiful blasts. We don't do comprehensive chromosomal screening. We say, we'll transfer this blast will freeze. We transfer, she doesn't get pregnant. We pick the wrong one. A month later, she comes back. In a natural cycle, we can transfer the thawed blast, and she gets pregnant. So her ultimate chance of pregnancy is the same without doing the comprehensive chromosomal screening. It may just delay things a little bit. Okay, now I can see I'm talking pretty fast. This is my last, near my last slide. This is the CRISPR-Cas9 revolution, okay? And I tell you frankly, I don't understand the genetics of this, okay? So don't ask me any questions about it. But basically, CRISPR stands for clustered, regularly interspaced, short palindromic repeats of DNA. And this DNA comes from prokaryotes, from bacteria originally. And Cas9 is an enzyme that splices DNA, okay? And so what you can do with this is a very inexpensive way to insert genes into embryos. And here's an example on a monkey. So the monkey had in vitro fertilization, an egg was collected, sperm injected. Here's the sperm nucleus. It's a little smaller than the egg nucleus. Then at this point, when the embryo was a single cell, they used this CRISPR-Cas9 technology to alter 2 genes. Okay, so the gene was altered in this nucleus, in that nucleus, 2 genes, so that the monkeys that were born had those 2 genes altered in every cell in their body, including their germ cells, the cells that will develop into sperm and eggs. So this is a permanent alteration in the DNA that can then be passed on generation to generation. And I have to show you the 2 cute little monkeys, okay? So as near as we can tell, all of their genes were successfully altered. Now, we don't know 100% for sure. And when these monkeys are older, they'll be bred to see if their offspring continue to have the altered genes. That brings up some concerns, okay? Because it is at least theoretically possible now, and it's been done in animals. In fact, rats who have an abnormal liver enzyme that gives them severe liver disease, they've actually altered the genes in the liver, so just in somatic cells, that produce that abnormal enzyme to cure the rat of that disease, which was induced in the first place. But there's a lot of concerns about this. And last April, there were editorials published in both Science and Nature by groups heavily involved in this technology that strongly discouraged any use of the CRISPR-Cas9 technology that would alter germ cells in people so that it would be passed on from generation to generation. And there's 2 reasons for that. One, we know the technology is really, really good, but we don't know it's perfect. And let's say in 1% of mice or 1% of monkeys, something goes awry and the DNA doesn't get put in the right place. Well, that's not going to matter so much. But if it's 1% of human embryos, it's a huge issue. The second thing is when we alter genes, we think we know what we're doing, but biology is so complex and you can't predict it. And so altering these genes may have unfavorable outcomes in other parts, in other aspects of the body that you can't predict. And so these groups very strongly recommended that this technology should not be used on human embryos to make any permanent alterations until we know a lot more about the technology and what can and can't go wrong. And I don't know if this is ever going to happen, but if I had to place a bet on it, I bet it will happen, and it will probably happen faster than I think it's going to happen. So I want to move on here. I forgot my first bit of advice. I was going to talk about, back in those slides that showed me deciding to go to medical school, did I already say that, my first bit of advice? So my first practical advice about how to prepare for the unpredictable future is, which is the short term. So to prepare for the unknown future, you have to prepare for the short-term future because you're better at doing that. So you just have to do the very best at what you're doing. And if you do that, then chances are you're going to survive better with these long-term, unpredictable twists of the future. But that's kind of limited advice. It's practical, but it's not, for the really big problems, it's not useful at all. Well, I'm going to move on here. So here is a small sample of birth announcements and Christmas cards and even birthday announcements that I've received from some of my patients. This is why I really love my work. I must confess, not all these are my patients. Here are my grandchildren right in the middle. And I had to put them in there because I'm so proud of them. But the letters that come with these announcements are, forgive me, I always cry when I talk, are very touching, very touching. And it makes me realize what a great blessing it's been in my life to help these people fulfill their dream of having families. And it makes me, it's a rare opportunity to do that. And our children bring us great joy and great sorrow. And I'm sure children can say the same thing about their parents. But they are the source of one of our, bring us such a tremendous amount of happiness. So all of this, and I'm going to move on to my second bit of advice now, has left me thinking about the story of Abraham. Now this is a panel from the door, the East Baptistry door of the baptistry in Florence. There were 12 panels, each one showing a scene from the Old Testament. They were done by Lorenzo Gilberti, A century later, Michelangelo called them the gates of paradise. So here is the panel showing on the left-hand side is this Genesis 18. Here's Abraham getting ready to wash the feet of the three angels who have come to tell him that he and Sarah will have a child. And here's Sarah in the tent door laughing at the thought of having a baby when she was 91, which, is a reasonable thing to laugh about. On the right-hand side is the dramatic story, probably the most dramatic story in the Old Testament of Abraham and Isaac. And here is the donkey and Abraham's servants at the base of the hill in Moriah. And here's Abraham, Isaac bound upon the altar, upon the wood. Abraham with his arm raised, his knife in hand, the last moment, the angel stopping him from sacrificing his son. So I've thought a lot about this story, as I'm sure you all have, many, many people have. And I've come to the conclusion, I'm just going to read this. What did God teach Abraham and Isaac through this heart-wrenching trial? I believe that he taught them in part that it was only through Christ's atonement that Abraham and his descendants could receive the blessings promised in the Abrahamic covenant. In the Jewish faith, this story is referred to as the Akedah, or the binding. Are we not all bound by our mortality and our sins? If there were no atonement to loosen these bonds, we would be sacrificing each child brought into this world to a meaningless death as surely as if we were to offer the child's life on the altar of a pagan god. Our lives would be without faith, without hope, and grim beyond telling. But God did provide a Savior for us who willingly atoned for our sins to bring to pass the immortality and eternal life of man. And every child who comes into this world comes with that hope. So this is the second answer to the question I posed at the beginning of the lecture. Each of us can prepare for the unknowable future by having faith in Christ. It is a slow but sure preparation for our future. I want to thank my family. So many, the room would be a lot emptier if my family were here. I want to thank my family, so many of whom are here today, so very much for all that they've meant to me in my life. And I want to thank you all very, very much for your attendance and your kind attention. Thank you.